my name is Raida Idayu and I will be explaining about what is absorption. So, it is the process by which one material, called the absorbent, is dissolved or completely taken into another material known as the absorbent. So, this process plays an important role in many areas of science and daily life. In pharmacology, it describes how a drug moves from its point of administration into the bloodstream. A drug's chemical composition, formulation, and route of administration all influence how well it is absorbed. So, there are different types of absorption. Physical occurs without a chemical reaction, such as gases dissolving in liquids. Chemical one involves a chemical reaction and bond formation. Biological one takes place in the living system, such as nutrient uptake in the intestines. Radioactive absorption involves materials absorbing energy from radiation. Together, these types highlight the wide significance of absorption across science, industry, and daily life.
Assalamualaikum and hi, my name is Abdullah Mehan, and in this video I'll be explaining about the fundamentals of absorption. So what is absorption? Absorption is a gas-liquid mass transfer process where a component in the gas phase called the solute is transferred into a liquid phase known as the solvent. This process requires direct contact between the gas and the liquid so that the solute can move from the gas into the liquid. Absorption is commonly used to remove unwanted or harmful gases from the gas streams. In a typical absorption system, there are three main components. The solute, denoted as A, is the substance that we want to remove. The carrier gas, denoted as B, is usually an inert gas such as air that transports the solute. And the solvent, denoted as C, is the liquid that absorbs the solute. Next is the gas-liquid equilibrium and solubility. When the gas and liquid are brought into contact, absorption does not continue indefinitely. Instead, the system will eventually reach equilibrium. At equilibrium, there will be no net mass transfer between the gas and liquid phases because the solute leaving the gas is balanced by the solute returning from the liquid. The relationship between the solid concentration in the gas and the liquid phases at equilibrium is described by Henry's law. This law shows that the solubility of a gas in a liquid depends on the nature of the gas, the solvent, and the temperature. Gases that have higher solubility in a liquid are generally easier to remove by absorption. The absorption process is driven by a concentration difference, also known as the driving force. The solid always moves from a region of high concentration in the gas phase to a region of low concentration in the liquid phase. When this concentration is large, absorption occurs rapidly. As the solid accumulates in the liquid, the difference becomes smaller, causing the rate of absorption to decrease. At equilibrium, the concentration in both phases are balanced, resulting in zero driving force and no further absorption. Therefore, the driving force naturally decreases as the absorption proceeds. In industrial absorption system, counter-current flow is commonly used. In this arrangement, the gas flows upward while the liquid flows downwards. This configuration helps maintain a high driving force throughout the column, leading to better absorption efficiency. Absorption can occur in either single-stage or multi-stage contact systems. In single-stage absorption, the gas and liquid contact only once, resulting in limited solid removal. In contrast, multiple-stage absorption allows repeated gas-liquid contact, which significantly improve the overall removal efficiency.
Hi everyone, I'm Tanush. So I'll be explaining about the simple demonstration of absorption using three different materials which are using wax paper, paper towels and sponge to see how much water can it hold. So firstly, which of it using wax paper. As you can see, after putting it into the water, it only absorbed of 3 drops of water itself. Secondly, is using paper towels. Paper towels are absorbs more than the wax paper itself and the drops soak right in it. Finally, using the sponge, it absorbs more water than the other two materials because of its porous structure. It clearly shows the difference in absorption capacity. So, from this simple experiment, we can see that the sponges absorb the most, and the paper towels are moderately absorbent, and lastly, the wax paper is partially non absorbent. This activity helps us to visualize the concept of absorption and understand them how material properties affect in real life. Thank you.
Let's take a look at the advantages and limitations of absorption. Let's start with the benefits. One of the biggest advantages of absorption is its high efficiency, especially when capturing particles or contaminants present at low partial pressures. This makes it extremely effective even when targeted compounds are present in small amounts. Absorption is also highly versatile. It can operate across a wide range of temperatures, pressures, and gas compositions, making it suitable for many different industrial environments. Because of this flexibility, it's often chosen for treating complex gas mixtures where multiple components need to be selectively removed. Another key advantage is simplicity. Absorption systems are relatively easy to install and operate, representing a well-established and mature technology. Furthermore, it's usually cost-effective, which is why companies prefer to use it for long-term operations. However, despite these strengths, absorption does come with some limitations. Most of the issues come from the solvent used in the process. Many solvents are corrosive, which means they can damage equipment over time and increase maintenance costs. In addition, solvents gradually degrade, reducing their absorption efficiency. When this happens, the system requires make-up solvent, and producing the make-up solvent may require a lot of energy. There is also an environmental consideration. If used solvents are not disposed of properly, they can contribute to pollution and create safety concerns. To better understand how absorption works in real life, let's take a look at a simple example. The chemical absorption of acid gases like hydrogen sulfide and carbon dioxide from natural gas using amine solvents like MEA, DEA, or TEA. This process requires relatively low operating costs and can remove up to 90% of carbon dioxide, even when concentration and partial pressures are low. But just as we discussed earlier, these solvents also highlight the challenges of absorption. Amines are highly corrosive and degrade over time, which means operators must regularly add fresh solvent to maintain performance. Overall, absorption remains a powerful and widely used technology, but understanding both its advantages and limitations is essential for designing and operating an efficient system.
Moving on to the fundamental unit operation of absorption, we will look at this concept through two very different lenses: a simple interaction we see in our kitchen every day and a complex critical process in chemical engineering industry. While the scale differ, the core principle remain the same: the transfer of the substance from one phase to another. We will start small with a household sponge and then scale up to the massive infrastructure required for natural gas dehydration. Let's begin with the everyday. Consider a common skinny sponge. When we wipe up a spill, we are witnessing physical absorption in real time. In this system, the sponge acts as a solid absorbent and the water is absorbed. The process is driven by capillary action. The adhesive force between the water and the sponge wall work together with the cohesive force of the liquid itself to pull water into the pores. This continues until the sponge reaches saturation, its maximum capacity, at which point it physically cannot retain any more liquid. Now, take those concepts and apply them to chemical engineering, specifically the dehydration of natural gas. When the gas comes out of the ground, it's often saturated with water vapor. We cannot put it into a pipeline like that. Why? Because moisture is a pipeline killer. If left untreated, water causes severe corrosion within the pipes, which is lead to the formation of hydrate, solid ice like crystal that can flow entirely. To prevent this catastrophe, we must remove the water. To do this, we use a liquid solvent called triethylene glycol or TEG. We choose TEG because it's hygroscopic, meaning it has a massive affinity for water. It is chemically stable and it doesn't evaporate easily. It is a perfect sponge for this industrial application. The actual absorption happens here in the absorption column. The process is elegant in its simplicity. We pump lean or dry glycol at the top, the wet gas enter from the bottom. As they pass each other in the counter current flow, the glycol physically absorbs the water vapor from the gas. By the time the gas reaches the top and ready to sell. But we don't just throw the wet glycol away. That would be expensive. Instead, we send it to a regeneration unit which will be absorbed. We heat it about 200 degrees Celsius, which is reverse the process, stripping the water out, and the glycol is now lean again, and it recycled back to the start. Is it a continuous and efficient loop?
In conclusion, absorption is an essential process that connects daily life experiences with advanced scientific and industrial applications. From a way a sponge absorbs water to how our body absorbs nutrients and medicines, absorption plays a crucial role in sustaining life and improving human well-being. Industrially, absorption is used in processes such as water purification, oil spill cleanup, and natural gas dehydration, where it helps to remove unwanted substances efficiently and economically. So despite its many advantages, absorption also presents challenges including solvent degradation, corrosion, and environmental concerns which require careful system design and maintenance. Overall, absorption is a powerful yet often overlooked process. By understanding how it works, we will gain a deeper appreciation for the science and behind everyday products, medical treatments, and industrial technologies that quietly shape our world. That's all from us. Thank you.